We move in the third part of this lecture to discuss cylindrical coordinate systems. But before I do that, I wanted just to remind you a few facts about Cartesian or rectangular coordinate systems. We know that every point in Cartesian coordinate systems will have three coordinates, x, y, and z. And this means that this point is actually the intersection of three planes. So here, you can see this plane here. This is a constant y plane. Y is equal to yb plane. This plane here is a constant x plane, and this plane here is a constant z plane. So the point is really the intersection of these three planes. If you have two planes intersect in three-dimensional coordinate system, it gives you a line. It doesn't give a point. And of course we talked about the position vector. We said the position vector is a vector pointing from the origin to the point. As shown here, we have two position vectors, OP, we call it RB or RQ. And you could see what is meant by RB to have coordinates 1, 2, and 3. This means that if you project it on the x-axis, the distance from this distance will be 1 unit. Maybe it's 1 meter, it's whatever the unit may be. You can see here in the z-axis there are 3 units, and on the y-axis it has 2 units. So again, it's the intersection of three planes, and the same applies here for point Q as well. There are three principal planes, three principal planes in the Cartesian coordinate system. The first plane is the z equal to 0 plane, which is the xy plane. The second one is the y equal to 0 plane, which is the zx plane, and then the third one is the x equal to 0 plane, which is the zy plane. And there are you can get other principal planes. So any plane x equal to constant is a plane that's parallel to the yz plane, but it's not exactly at 0. So for example, I can draw another plane here. This plane is indeed parallel to the yz plane, but it has a different x. It's a plane x equal to a constant, and so on. And there are something called principal lines. Principal lines are lines parallel to the principal axis. For example, here a principal line given by x equal to constant and y equal to constant. This is the intersection of two planes. The first one, x equal to constant, is parallel to the yz axis. Y equal to constant is parallel to zx axis. So their intersection will give you a line that is parallel to the z axis. So z can vary from minus infinity to infinity. And the same thing applies for the other ones. Of course, the line x equal to 0, y equal to 0, this is the intersection of two principal planes equal to x equal to 0, y equal to 0. This is the z axis. The line y equal to 0 and z equal to 0, this is the intersection of these two principal planes. It is the x-axis. The line z equal to 0, x equal to 0, it is simply the y-axis. In Cartesian coordinate systems, we agreed that x, y, and z can vary from minus infinity to infinity. We can define unit vectors ax, ay, az. They are orthogonal to each other. Each one of them is pointing in the direction of one of the coordinates. The position vector of any point is written as a summation of x, ax, y, ay, z, az. And we agreed that the position vector does define a line because it has a reference point, which is the origin. While for any vector, in general vector, ax, ay, az, it has three components, and it can be written either this way as three components between brackets or expanded in this form. We needed this introduction or these reminders of the Cartesian coordinate systems to move to a new type of coordinate systems, which is cylindrical coordinate systems. Cylindrical coordinate system says that any point in space is given by three quantities. The first one, which we call ρ, so it is shown here, it is the orthogonal distance from the z-axis to that point. So this angle here is 90 degrees. The second one is the angle phi, and this phi here you should understand it is the angle between two planes. Phi is shown here is the angle between two planes. The zx plane, which is this plane here, okay? And the second one is the plane containing the position vector of the point r and the z-axis. So it is this plane here. So we have the angle between these two planes is the angle phi. Okay, so I'm sorry my handwriting is not very accurate, but the angle here is this phi. And the third one is how high it is from the xy axis, so this will give you z. So by knowing rho, by knowing phi, and by knowing z, we can completely determine the location of the point in this space. Now, in the same way we did for Cartesian coordinates, we have a unit vector a rho, which is pointing in the rho direction, a unit vector az, which is pointing in the z direction, and a unit vector a phi, which is pointing in the phi direction, and they are normal to each other. Notice that a phi is normal to this plane here. A phi is normal to the plane containing the position vector. So you can see this plane here. I'm trying to hash here. This is a phi is normal to this plane. And of course, you can convert from rho to z to x and y and so on. First I'll start by showing you this transformation. I will start by maybe drawing a line from the origin, which is here, to my point, which is here. This line here is really the position vector. The length of this position vector, which we call small r, and we'll be using this later, is nothing but square root of x squared plus y squared plus z squared. What is the relationship between r and rho? Notice this angle here, which r makes with the z-axis, a very important angle we call theta. r sine theta is equal to rho. If you project the vector r, sine theta will give you rho. What's r cosine theta? R cosine theta is z. Okay? So once I know what is x, y, and z, I can get r. R is the distance from the origin. This is one way of doing it. I'll show maybe a simpler way later. And if I know the angle theta with the z-axis, the angle between r and the z-axis, I can simply say that rho is r sine theta. Once I know rho is this length here, and it's as well the length from the origin to the projection of the point. So this length here is also rho. Okay, so if you project this if you know the angle phi, if you project it in this direction, you get x. If you project it in this direction, you get y. So we know that x is equal to rho cosine phi, and y is equal to rho sine phi. Now, the position vector r, and this is a little bit different from Cartesian coordinates, does not have a component in the direction of phi. It's given only by two coordinates, rho, a rho, and z, a z. Why is that? It's simply coming from this figure. Notice how a rho, which is pointing in this direction, is normal to the plane containing the z-axis and the vector r, the position vector r. So it is normal to the position vector. So the position vector cannot have a component in the direction of a phi, which is a little bit different from what we had in Cartesian coordinates. One other thing, a rho is not a constant. You have to understand this. A rho is not a constant. A phi is not a constant. They change from one point to another. So we can express them in terms of ax and ay, but this will give us a variable expression. For example, here, if someone looks from the top here, okay, someone looks from here, he will see the xy plane. So this will be x, this will be y. And at this point, this is the direction of the vector rho. This will be the direction of the vector rho. It's not being drawn accurately here. At some other point here, say this will be the direction of a rho. At some other point here, this will be the direction of a rho, and so on. So a rho is varying. As the direction is varying from one point to the other. Of course, a phi is always normal to a rho. So it's normal here. It's normal here. It is normal here, and it depends also on phi. So to summarize this slide, you can determine the coordinates of a point by knowing its normal distance from z-axis. We call it rho. By knowing the angle, its plane, position vector with the z-axis make with the z-axis, we call this angle phi, by knowing its z-axis. And the position vector is given in terms of rho and z components. There is no phi component. And you can express all this in terms of x and y. Similar to Cartesian coordinates, we know that rho is the normal distance from the z-axis. So if I draw the normal distance, this angle is 90 degrees. Rho can extend from 0 to infinity. So rho can have any values from 0 to infinity. It cannot be negative. Phi, this angle, which if I project the point B on the xy axis, I give this point, and this line from the origin will make an angle phi. So you have this line here, you have this line from the origin, makes an angle phi with the x-axis. Phi, of course, can increase from 0 up to 2 pi. You can move the point all the way around this circle to 2 pi. Z can be anything from minus infinity to infinity. A vector in general can have three components: a rho, a phi, and a z. But a position vector does not have a phi. And I explained earlier why. Because if you could take a look here, a phi, which is pointing in this direction, is normal to the plane containing the position vector and z. So the position vector cannot have a component in the direction of a phi. Now, if you want to get the magnitude of the vector, as I explained earlier, for Cartesian coordinates, and because these are orthogonal coordinate systems, the modulus of the vector is the square root of the sum of all its three components. So if you have electric field, it can have a rho, a phi, a z. Its strength, how strong it is at one point, is equal to the square root of the sum of the squares of all its components. Now, the unit vectors in the direction of rho, z, and phi, as we had before for Cartesian coordinates, they are mutually orthogonal. So if you do dot product between any two different ones, you get 0. And because they are unit vectors, and if you have magnitude of 1, and each one of them makes an angle of 0 itself, the dot product between one vector and itself will give you a unity value. One important thing that we'll see in this course is if I give you a function of rho, phi, and z, how you convert it to a function of x, y, and z, or the other way around. And this function can be any component of a vector. So how we can do that? This figure explains what's happening. If you have this point here, the point here is a function of x, y, and z, and it's also a function of rho, phi, and z. How do I do the conversion? Very simple. Project this point to the xy axis. To get this point, I will call it here b dash. The rho is the distance, as you could see here, from this point. So the distance of the projection from the origin. So rho cosine phi will give you x, rho sine phi will give you y, and z is the same. Z in the Cartesian coordinates is the same z in the cylindrical coordinates, so it doesn't change. How do we this? So now we can convert from cylindrical to Cartesian. How do the other way around? Very simple. If I know x and y, remember that this angle here is 90 degrees. Okay, if I know x and y, then rho in this triangle here. So this one here is y, this one here is x. So this is a right angle triangle. It's square root of x squared plus y squared. Phi is the angle facing y, and it has x as well. It's triangle. So from this edge and this edge here, we can simply say that phi is the inverse tangent of y over x. And remember that this angle phi here, remember that this here is a right angle in this triangle. Okay, z is the same, it doesn't change. So we can convert any function of x, y, and z into a function of rho, phi, and z by using these transformations. Or we can convert a function of rho, phi, and z into a function of x, y, and z. You can do it in both directions. Another problem that faces us when we rewrite vectors in cylindrical coordinates is that we have to transform the unit vectors as well. Remember that a rho is varying. A rho changes from one point to another. For example, in the figure to the left, this is the point at which we are calculating a rho. A rho is pointing in the radial direction. If I take some other point here, a rho will have a completely different direction. A rho, if I draw a line to the origin, this will be the direction of a rho. So a rho does change from one point to another. So if you have a vector, it's expressed in terms of a rho, a phi, and az. In order to convert to a vector in terms of ax, ay, and z, you must convert also the unit vectors. How we do that? Take a look at this figure. This figure shows a projection on the xy plane. So a rho has been projected on the xy plane. Remember that A rho changes, A phi changes, but AX and AY, they do not change. AX, as you could see here in this horizontal line, I'm going to be drawing it again in red. AX is pointing direction of X-axis, it's a constant. Because phi is the angle that the projection of the point on the XY plane does with the X-axis, if this angle here is phi, then this angle here is also phi. Then AX can be projected into two parts, cosine phi in the direction of A rho, notice this angle here, and sine phi in this direction here, this direction which I'm going to be drawing it in red. But this direction is not the direction of phi, this is the direction of minus A phi, because A phi points in the direction of increase of phi. So this is A phi, so minus A phi. So AX can be in general written as cosine phi A rho minus sine phi A phi. The same thing you do it in this figure, in the second figure here, with respect to the y-axis. Remember, the direction AY does not change, it's fixed. So I'm going to be drawing it again, it draws in the direction of y. If this angle here is phi, then by simple analysis, you can know that this angle is also here is phi, this angle here. So this is telling us that A rho, AY can be decomposed into two components. Cosine phi in the direction of A phi and sine phi in the direction of A rho, the radial direction. Okay, remember this is a projection from the 3D case. So I projected the unit vectors from the general 3D dimensional case, the XY plane. So this will give us that AY is equal to sine phi in the direction of A rho and cosine phi in the direction of A phi. AZ does not change, which is good. So now if I give you a vector which has three coordinates, AX plus AY plus AZ, and then I ask you to determine what is the corresponding coordinates, what are the corresponding components of that vector in the cylindrical coordinate systems, what's A rho, A phi, and AZ, you use these transformations. Here I decided to show you the detailed explanation. So this is the original vector in Cartesian coordinates. Of course, if AX is a function of X, Y, and Z, AX, which is this component here, I will also convert it as a function of rho, phi, and Z, but this conversion of function, not of a vector. And what I did, I took the unit vector in the X direction and I expanded it in terms of A rho and A phi, as shown here. And then I expanded the unit vector in the Y direction in terms of A rho and A phi. And then I will collect all the terms related to A rho, A phi, and AZ. So you could see now this term here is a component direction of rho. This term, the component direction of phi. This is a new Z. And so this is telling you that the component direction of rho is a function of the X and Y components. Component direction of phi is a function of the X and Y components. And component direction of Z does not change. And of course, you can put this in this matrix form. It's not that difficult to see from this form that A rho is equal to cosine phi AX plus sine phi AY as shown here. And the same thing applies for A phi. So this will take you from the Cartesian coordinates of a vector to the cylindrical coordinates of a vector. And remember, AX, AY, and AZ will have also to be written in terms of rho, phi, and Z. You can do the other way around. If you multiply by the inverse of this matrix here, if I call this matrix the transformation matrix T, it's not that difficult to show that this matrix its inverse is T minus 1 is given by this one here. So this is T minus 1. And this T minus 1 here, if you multiply T and T minus 1, you get the identity. It's actually an orthogonal matrix where every row is normal to all the other rows. So once you have that, you now in this expression here, you can convert a vector, three components of a vector from rho, phi, and Z to its components in the X, Y, and Z. Rho, phi, and Z to X, Y, and Z. And I want you to remember what phi means. Phi has nothing to do with the components of the vector. It is the point at which you are converting that vector. It is related to the point at which you are making a transformation from the X, Y, and Z coordinates to the rho, phi, and Z. So, for example, here, this is a vector A. It is in one Cartesian coordinates. I want to know at this point B, if I call this point B, how it is written in the cylindrical coordinates. So phi is related to the point B, is not related to the vector itself. So in this transformation, in this matrix here and this matrix here, you have to keep in mind that phi is related to the point at which you are making the transformation, not the vector itself. Now by giving you an example, we are given a point B which has three components, 3, minus 4, and 2, and a vector A which has three components, 2ax plus minus 3ay plus 4az. We want to express B and A in cylindrical coordinates and evaluate A at B. Of course, this is direct application. These vectors look very nice, very easy to write in Cartesian coordinates. But in cylindrical coordinates, they're going to be way more complicated. Because remember, x, y, and z, they are constant coordinates, while rho, phi, and z, they change. They change direction with phi. So it must be dependent on phi. So let's take a look at this transformation. Here at the point B, we have that x equal to 3, y is equal to minus 4, and z is equal to 3. To convert to coordinates is pretty straightforward. You calculate rho. Rho is the radial direction, square root of x squared plus y squared, square root of 3 squared plus 4 squared. This will give you 5 here. Phi is the angle whose tangent is y over x. So it's minus 4 over 3, and from the properties of inverse tangent, it is minus the angle whose inverse tangent is 4 over 3. And if you do this using a calculator, you get 53, so the answer is minus 53.1. And of course, because this 2 pi, it repeats itself, it's 2 pi, the total answer is 306.9. So we know that the point B in cylindrical coordinates has coordinates rho equal to 5, phi equal to 306.9 degrees, and z is the same, it's equal to 3. So the results shown as here. Now we can convert the vector A as well. In order to convert the vector A from Cartesian to cylindrical, we use the transformation matrix. And again, you don't have to remember this transformation matrix, but you should know how to use it. And remember here that phi, this angle phi in this transformation does not depend on the vector components here. It depends on the point at which you make the transformation. So if you multiply the expansion, you get that A rho is equal to 2 cosine phi minus 3 sine phi. You get that A phi is equal to minus 2 sine phi minus 3 cosine phi, and z is the same. Z does not change from Cartesian to cylindrical. So now, if in order to calculate at the point B, we know that the phi is equal to 306.9. This angle, because it is the inverse tangent of minus 4 over 3, it has a cosine of 3 over 5, and it has a sine of minus 4 over 5. If you remember the triangle, this famous triangle here, if this is 4, actually should do it the other way. Yeah, this is 4, this is 5, this is 3, this is 4, and this is 5, and this here is the angle theta is 53 degrees. So this is why I immediately wrote the cosine as 3 over 5. The sine at this point is minus 0.8. So at this point, phi is equal to 306.9, cosine is equal to 0.6, sine is equal to minus 0.8. So now we take this and substitute in the expression for A rho, A phi, and AZ to determine the components of the vector A in cylindrical coordinates at this specific point. If you do that, you get the following answers. Pretty straight substitution. Replace every sine phi by minus 0.8. Replace every cosine phi by 0.6. So you get the answer that A rho is equal to 3.6. This vector has a component at the point B of 3.6 in the rho direction, a component of minus 0.2 in the phi direction, a component of 4 in the z direction. So it can be written in this way here in cylindrical coordinates.